Our third part of Chapter 8 takes us into what is kind of an extension of the normal curve, and it's this concept of z-scores. If you understand the normal curve, and you understand standard deviation, and you understand proportionality, you'll get a good handle on z-scores. Now, z-scores are a little bit more complicated in the sense that we actually have to calculate them. But then we also have to understand what they're useful for. And so there's two things that they're useful for. One of them is allows us to compare, as you will see, scores from different scores that are of different units from different distributions together. That might not make a whole lot of sense right now, but hopefully it will. And the other thing with z-scores, again, similar to what we saw with the normal curve, it also allows us for more what I call more refined probability predictions of where scores might occur. So z-scores are also called standardized scores. Okay, you'll see that in the literature. You might see something called a standardized score, and that means it's a z-score. And you will see z-scores in the literature from time to time. Not often, but from time to time you'll see z-scores. And so the question I have on here on this slide is the question, can we really compare apples to oranges? Well, on the surface, no, right? You can't. And that's that old saying, well, you can't compare apples to oranges. You can if you can convert them to z-scores. And so what z-scores do is they take different units of measurement, let's say height and weight, right? And they convert them to some sort of universal scoring method or standardizing a score so that height and weight can actually be compared, right? Now the units that are measured with height and weight are very different. Height is a measure of, I guess it's a measure of length, I guess, and weight is a measure of force. While force is measured in newtons and height can be measured in meters, they're very different units of measurement. But if I can convert height and weight or standardize their scores into something else, then I can compare the two. And what we do is we take the measures of height and the measure of weight and convert them into z-scores, and then I can compare the z-scores together because I'm using the same unit of measurement. I've standardized the unit of measurement. Now, the one thing I'm going to tell you right now to make it easy with z-scores is that and listen to this carefully, please, a z-score is the same thing as a standard deviation unit. So one standard deviation is the same as one z-score. If you can get that, everything else is going to fall into place. The only difference, and we use the same normal curve too, as a matter of fact. So we use the same curve, and all we do is change, instead of having standard deviation units, we have a z-score unit. The only other thing that changes, as you'll see, is that the mean value, whatever the raw value for the mean is, we convert that to 0. It's kind of like zeroing the scale, so to speak, and then using the same units of measurement, in this case, z-scores. So some measures are pretty straightforward. As a matter of fact, some measures are actually meaningful. So for example, if I measure the length of an object in meters, right, this is the international system of units that we use, the measurement obtained is meaningful. We know that meters is a measurement for length. And that length is going to be, the length that we actually take is going to be the same whether it's by your meter stick or mine. I've got yard on there on the slide, but it should be meters. So we can actually compare the measures, right? You're measuring meters, I'm measuring meters. We know what a meter is. It's a unit of length. And so we have some understanding of how long a meter is, right? That's pretty straightforward. You're probably telling me, tell me something I don't know. That was a useless slide. Well, hang on a second. Let's go take a look at the next slide. But what if I wanted to measure something a bit more complex? Things like intelligence, or for my field, physical fitness, right? If I'm measuring someone's physical fitness, what exactly am I measuring? Well, we have to define what physical fitness is first, and what we find when we do our definitions, if we kind of drill down, we find that there's more than one domain or more than one facet of physical fitness. Like there's a series of facets or a series of domains, different domains that actually describe what physical fitness is. And these domains include things like, this is just 4 of them, there's more, things like aerobic capacity, how much oxygen they can take in, their power that they can push out, upper body, lower body, you take your pick. Issues like flexibility or range of motion, body composition, all of those have different units. Aerobic capacity is in liters per minute. Power is in watts. Flexibility could be degrees or radians if I'm looking around a joint. Body composition is measured in percentages. They're all different types of measures, right? But taken together, these domains collectively give us a sense of a person's physical fitness. But the issue is they all have different units of measurement. So how do you want to compare things like aerobic capacity to power? How do you compare those if they're different units? This is why we're talking about comparing apples and oranges here. So unlike the measurement of length, where one quote-unquote yardstick of physical fitness is not the same as the other, right? We can use something called a Z-score or a standardized score to actually compare 2 different aspects that have two different units of measurement. What we do is we standardize those scores into one single type of score. That's what we do, and that's called the Z-score. So we convert these measurements into the same measurement variable, if you want to think about it that way. So aerobic capacity, which is measured in liters per minute, the amount liters of oxygen per minute, is converted into a Z-score. Body composition, which is measured in percent body fat, in this case, would be converted into a Z-score. So now what I've done is, now because I've done this, I can now compare Z-score against Z-score because they're the same unit of measurement. So you might be asking, how are these Z-scores useful? Actually, I know you're not asking this. You're probably asking, why do we have to do this? Mike, you're killing us. I know, I apologize. But we need to forge ahead. Hey, so Z-scores can do a couple things. This one we've already been talking about. I can take 2 different units, right? 2 different measurement units from 2 different distributions, and I can compare the 2. Why? Now I'm using the same measure, right? And I'll give an example of that coming up. That one isn't, I think for us in this course here, that's not as important as the second one. You'll see that from time to time in the literature if you read a lot of it. I haven't seen it a lot. Z-scores do pop up in the scientific literature. I don't see them as much. But the second one here is probably more important for us in terms of our understanding of statistical significance, and especially for measuring different scores, okay, or measuring differences between 2 means. The second one is more important. Z-scores allow us to calculate the probability of a score occurring within a normal distribution. Now you might be thinking, if you didn't fall asleep in the previous couple of PowerPoints with Chapter 8 and the normal curve, we've kind of seen that already, haven't we? Well, we have, and we're going to unpack that. So we're going to extend our knowledge a little bit of the normal curve by talking about Z-scores. So Z-scores extend a little bit more what we already know of the normal curve. So really it's a small step sideways. Bear with me here. With the Z-score, what we do is we take a normal curve, the ones you've seen before, and notice what we had before in the middle with the normal curve. If you took a look at the mean is always represented by that mean score, and then you've got the standard deviation units. Well, we have to standardize that mean, whatever that mean value is. You'll see it on the next slide coming up. And what we do is we zero the normal curve. You want to think about it this way. If you've ever had to do chemistry, for example, you always zero the scale before you put something else on it. We're kind of doing that here with the normal curve, where we're taking the mean, all means of any distribution where we're looking at, and we convert that to a 0, right? And then after that, we simply change every standard deviation unit to 1 Z-score, right? So 1 standard deviation away from the mean would be 1 Z-score from the mean, okay? And the reason why you can compare two different distributions that have two different types of measures is because both means are now set to 0. You're not comparing 100 to 250 if there was two different means. You're comparing 0 to 0. What you really want to compare is what z-scores you're. So this is what a normal curve looks like when it's been converted to z-scores. And really there's no difference. As a matter of fact, if you take a look, right, the normal curve holds true. And if you take a look at the distributions, they're slightly rounded here, okay, so don't worry about that. The normal curve distributions, right, which used to be, one standard deviation here, we've now converted all the standard deviations, right, to z-scores, right? We've zeroed the scale, we've taken the mean, and we've taken the mean to 0. And what we do now is we've converted all the standard deviation units into z-scores. All the proportionality under the curve still stays the same. Nothing really changes. The only thing we've changed with the normal curve here is the bottom part. We've taken the mean, set it to 0, right? We've zeroed the normal curve, right, from the mean, and we've converted all the standard deviations into z-scores. So, in other words, if a score on the normal curve lies 1.5 standard deviations above the mean, that z-score would be 1.5. If a score on the normal curve lies at minus 2.0 standard deviations below the mean, the z-score would be minus 2.0. Again, note that z-scores can be positive or negative depending upon which side of the now zeroed mean they fall on. Positive z-scores fall to the right, negative z-scores fall to the left. I should have warned you on the previous slide that some math was coming up, but again, the math isn't that challenging, right? It's not that challenging. It's another fraction. I told you, a lot of statistics is fractions, and this is even a less stinky fraction than that really nasty variance fraction. Remember that? That was awful. So this one's not too bad. But we have to actually get into dig a little bit deeper here and actually get at, well, how does one calculate a z-score? And this is our fraction here, and it's pretty straightforward. In the numerator, all we have is the raw score, the individual score in a sample, right? And from that, we subtract the mean of that sample from the raw score. We saw that before in variance, right? Notice this time that we're not squaring it. And we divide it by there we go. We divide it by the standard deviation. That's how you get a z-score. And you can work these things forward and backwards, right? As long as you've got 3 pieces of information here, you can solve for the 4th, right? If I want to know what a z-score was, and I'll give some examples. You're gonna get some practice examples too for this section. Z-score was, and I knew what the raw score was and the mean score and the standard deviation, I could tell you what the z-score was. If I gave you a z-score and I gave you the standard deviation and the mean, you could solve for the raw score. So as long as you've got 3 of the 4 pieces of information here, you can solve for the one that is not given. So you can run these equations backwards and forwards. I think your other question might be, why would I ever do that? Good question. We'll talk about that a little bit. So let's do an example, straightforward example. Calculate the z-score if you had a raw score of 100, whatever that unit was, meters, kilograms, whatever, doesn't matter. Raw score of 100, a mean of 120, and a standard deviation of 10. Well, I've given us our equation here, right, to calculate the z-score, and let's do this. So when I work on the equation, here my z-score again is equal to the raw score 100, yeah, minus the mean, right, which is 120, so I've popped that in here, beautiful, divided by the standard deviation, which is 10, so 10 is popped in there. So when I work this out, I get minus 20 over 10. Again, remember, it's okay to have a negative value because you're dealing with the normal curve and you've got positive and negative z-scores, right? So don't worry if you've got a negative value. It just tells you on what side of the zeroed mean it's going to fall. And 10 into minus 20 is pretty straightforward. It gives us minus 2. Okay? So that's what the z-score is. And where would that fall on our normal curve? Well, it's going to fall right about here. This is where you would fall compared to everybody else in that normal distribution. If your score was 100, if the mean of that sample was 120, the standard deviation was 10. I could tell you where you fell in that class. I've often joked with my students before in the past. It's not a funny joke whatsoever. I'm just trying to be sassy, where I threaten them sometimes and I say, you know what, one of these days I'm going to give you your midterm score in z-scores. I'm going to give you the mean and the standard deviation, and you can go figure out your raw score. That's never accepted very well for some reason. I'm not sure why. So I want to do an extended example for you. So this is going to be perhaps painstakingly detailed, but I want to go through this slide by slide because I know that math for some is still, it's math, and you got to struggle with it. I get it. I totally get that. So I'm going to go and show you an example of comparing two different scores, one from a math test and one from a verbal test. And the question is, you know, where did you fall compared to the rest of your classmates? So suppose you scored 65 on a math test and 30 on a verbal test, okay? Now, on which test did you perform better overall, and how did you compare to your classmates, right? Now, you just might be interested in, well, what was my percent, right? Did I get an A or not? That would be my question. Okay, I don't care how I compared to everybody else, right? Did I get an A? Did I get 85 or not? Right? Or did I pass, or did I fail? Those are the real life questions from students. But you've got to put your mindset in the mindset of a researcher, where you're comparing things against everybody else, right? Because again, these normal curves are supposed to represent populations, right? So where'd you fall compared to the rest of the class? In this case, it's going to be the population. Those things interest researchers. It's not going to interest you because you want to know your grade, but nevertheless, here we go. So we're going to do two things, actually. We're going to assess on which test you performed better overall. Are you better at math? Or are you better at verbal skills? And how you fared on both exams relative to the others taking the exam. In other words, how do you compare to your classmates? Okay. So before we get into this example, we need some information first. So here's how you did. The mean score on the math test was 50, and you scored 15 points above the mean. Okay. The mean score on the verbal test was 20, and you scored 10 points above the mean. I mean, so far the good news is you're better than average, right? You're scoring better than half the class at least. We just don't know by how much yet. Can you conclude that you did equally well on both tests? Because I mean, you're above the average in both the math test and the verbal test. Now you want to do the comparison between the two. This is where we start comparing apples and oranges, right? The thing is, you don't know, because you don't know if 15 points on the math test is the same as 10 points on the verbal test in terms of where you place. So we have to convert these things into z-scores. Before we get into the calculation of the z-score, we need a little bit more information, and that has to do with the standard deviation. So let's say that on the math test, the standard deviation was 15, and on the verbal test, the standard deviation was 5. Now this gives us a little bit of information in terms of the spread of the scores. Notice that you can have scores where the variance is different. And so we need that variance to actually calculate the z-score. Now what's really helpful is if you can graph this stuff, right? But a lot of times graphing, you don't get that option. They don't give you the graph. But if you could graph it, right? If you had all the data in graph it, here's what we have. So again, here's our means. Now notice we haven't converted these to z-scores yet because these are still the raw scores, but the means have been lined up. Okay, and so we see that the spread of the scores in the math test, right, is rather wide. That would be, what type of curve would that be? Do you remember that from chapter 4? Begins with a P, right? It's a type of mammal that lays eggs. That's where we get the root from, right? What is that again? You're right, platypus. No, it's platycurtic curve, okay? Now the verbal test down here, the curve looks fairly normal. But notice, and this is what we would expect because of a smaller standard deviation, the scores are closer to the mean. Okay, so let's see where you scored on both these scales here. So if we take a look at your math score, right, you scored 15 points above the average, which is 50. And it just so happens, right, that the standard deviation was 50, and so this is where you scored here, right? That's you. And so you scored, because the standard deviation was 15, and you scored 15 points above the mean, you scored 1 standard deviation above the mean, right? So that's going to give you a value of 65. The verbal test down below, you scored 30, okay? And what that means is you also scored 10 points above the mean, which means that you scored 2 standard deviations above the mean, because the standard deviation for the verbal test was 5, and you scored 10 points above the mean. So this is where you're holding on both scales. Okay, so let's calculate the Z-scores here. So here's your raw score, 65. On your math test, we want to convert that to a Z-score. Let's get our little formula up there. That's lovely. And so we actually run the values through, right? The raw score minus the mean. Here's our raw score minus the mean score divided by the standard deviation. We get a Z-score of 1.0. Okay, so this is where you're holding here. Now the verbal test down below, let's see where you scored. Now remember, you scored 15 points higher on the math test than you did on the verbal test, right? Verbal test, you only scored 10 points higher than the mean. So on the surface of the raw scores, it looks like you're better at math than you are at the verbal scores because you had so many points higher. But let's take a look at this when we actually convert the verbal scores into Z-scores. So you scored 30 down there. When you run the Z-score here, you actually scored 2 Z-scores higher than the mean, compared to 1 Z-score higher with the math test. So in actuality, you performed better on the verbal skills test than you did on the math test, only after we've zeroed the mean and changed both the math scores and the verbal scores into Z-scores. We standardize them. Then you can do a level of comparison. You're much better at verbal stuff than you are with the math stuff. Okay, so I've kind of said this on the previous slide, but here's some of the verbiage to kind of slow this down. And so again, you scored 1 Z-score above the mean for the numerical test, and you scored 2 Z-scores above the mean for the verbal test. So we've answered the first question. On which test did you perform better overall, the verbal or the numerical test? And the answer is the verbal test. Now the second question is, how did you fare on the exams relative to the other people taking the exams? So how did you compare to everybody else in the class taking those tests? Let's answer that question on the next slide. So just for visual stuff, I'm a visual learner, so this is mostly about me here. I'm kidding. So here's where you were with your numerical or your math score, right? And here's where you were with your verbal score. Because we're now using the same units of measurement, because they've been standardized, you can put the where you scored numerically, your math score and your verbal score, on the same curve. Okay, that's what you can do. So this is where you are now that we've standardized everything, right? We've changed that mean to 0, right? And now we're both comparing your math score and your verbal score based upon Z-scores. We can now see that you did quite better verbally than you did with your math side of things. So visually here, we see that red line. Now it's not quite lined up with the Z-score, but it should be 1. This is where you scored compared to everybody else. Now, if we take a look at the normal curve and we know the proportions under the curve, that can actually get a sense of what your percentile score is, and that's on the next slide. So how did you do compared to everybody else in the class? Like I said before in the previous slide, we can actually work out your percentile, right? Or how many people fell below you, how many people fell above you, if we know what your z-score is. And so we see that because you scored one z-score above the mean, that means that 84.13% of all the other scores fell below yours. That means that you scored in approximately the 84th percentile in the math class. That's actually not too bad. I'd be pretty happy with scoring in the top 84% of my class if it was a math class. When we take a look at your verbal score, we know that you scored 2 z-scores higher than the mean. And this tells us as well, again, where's my little red pointer here, little laser pointer, pardon me, there we go. So this is where you scored here, right? Again, this is the distribution of all the marks in your class, and this means that you scored here, which means a very small percentage of folks actually did better than you in the class. As a matter of fact, I can add this up here. Only, 2.28% did better than you in the class, which means that all this other percentage here, I'm not doing the math in my head. What's 100% minus 2.28? That's on the next slide. But if you were to take a look at the area under here, the proportion, it's well above 97%. So you're scoring close to the 97th percentile in the verbal aspect of the test. And so here we go again, right? So I think I said before in the previous slide, because you scored 2 z-scores higher than the mean, that means that you scored better than 97.7% in the class itself. Only 2.28% of your classmates scored better than you. So you were close to the 98th percentile in that verbal test, which is absolutely outstanding. That's like A+ range. Good for you. So let's finish up with the summary here, and I guess I'm ending a little bit abruptly, in part because I think your brains are kind of full. We've covered a fair amount in this section, and I hope you're still holding on. So again, just to kind of summarize what z-scores can do, right? They allow us to compare. They allow us to compare apples to oranges. I've got 2 different units of measurement. If I convert them to z-scores, I can now compare the 2 because they're using the same unit of measurement. I can even throw them onto a normal curve and see where they fall on a normal curve, and that allows us to see which area we can do better. I mean, think about, you know, if you're measuring something like intelligence and you're measuring 10 different dimensions, you could convert all those 10 different dimensions, all those individual types of different units of measurement, convert them all to z-scores, and you can see exactly where that person is falling in terms of how well they do, either compared to others or compared to the different dimensions, right? That's the other thing that you can do with these things. That's the first part there. Z-scores enable the researcher to compare 2 scores from different normal distributions. The other thing that they can do, and we touched on this more with the normal curve itself and standard deviations, is the probability of a score occurring within a normal distribution. But it gets a bit more complicated, and you need what's called a z-table to do that. If you noticed with the math score and the verbal score, the z-scores that we calculated were really sanitized, right? I mean, the math score was 1 z-score above the mean. The verbal score was 2 z-scores above the mean. There's an awful lot of numbers in between 1 and 2. So what if I were to ask you a question, well, what's the probability of a score occurring, you know, between 1.4 and 1.72 z-scores above the mean, right? That's much more complicated because now you're calculating the area under a partial curve, and so you need the math to do that. The good part is there's a series of tables that have been developed to tell you exactly that. And I didn't do that in this presentation, again, mostly because I think your brains are probably full, and I think that just might be the tipping point for this week. And so I left that off. When I teach face-to-face, we do it together in class. We spend about 20 minutes, half an hour working together on some examples. We slow it down. And I just don't think, I think it would be a real mess if I were to do it through PowerPoint here. Even a Zoom lecture, I thought about it and I'm going, this could be a dumpster fire. Regardless, what I'm going to do is I'm going to post the Z table, and I'm going to post a little Diddy on how to do that, and if those